Welcome, listener, to another deep dive. Today, we're getting into Hi3DGen. This is a really interesting AI that generates incredibly high-fidelity 3D models from just one 2D image.
That's right.
Our mission today is really to unpack how it works, its unique approach, and, what it actually means for you, the creator.
Exactly. And our sources show Hi3DGen is tackling head-on one of the big persistent problems, getting really detailed 3D geometry out of a flat picture. That's where it gets fascinating.
Okay, let's unpack that then. Why has this been so hard? Generating detailed 3D from a single 2D image, it feels like something we should have cracked ages ago, right?
Well, the core issue is ambiguity. A 2D image just leaves so much out.
Like lighting, shadows.
Precisely. Is that dark patch a dent or just a shadow? Current methods really struggle with that. Plus, honestly, there's been a real shortage of high-quality 3D training data that properly links 2D views to complex 3D shapes.
The data bottleneck.
Always a factor. But what's really clever here, the core innovation with Hi3DGen, is something they call normal bridging.
Normal bridging. Okay, that sounds intriguing. Like a workaround. How does that function?
It's exactly that, a very smart bypass. It uses normal maps as this intermediate step. Now, a normal map isn't just a picture. Think of it more like a 2.5D representation.
2.5D.
Yeah, basically each pixel's color tells you the precise orientation of the surface at that point. Like which way is it facing? It's like a cheat sheet for the geometry.
Okay, so it's encoding the direction of the surface everywhere.
Exactly. It provides much, much clearer geometric information, way less ambiguous than just looking at light and shadow in a photo.
Got it. So with this normal map as its guide, how does Hi3DGen actually, build the detailed 3D model? What are the steps involved?
It's really a neat three-part system working together. First up, you've got the image to normal estimator. They call it NIRN.
NIRN. Yep.
Its job is to do that first translation, take the input 2D image, and generate that sharp, stable, normal map we talked about. It uses some clever techniques like noise injection.
Which helps it handle real-world imperfections.
Right, makes it more robust. And also dual stream training, processing information in parallel pathways to get really accurate results.
Okay, so NIRN creates the blueprint, the normal map. Then what?
Then that map gets handed off to part two, the normal to geometry generator, or NORAL-D.
NORAL-D. So this is where the 3D shape actually comes from.
Yeah, this is the sculptor, yeah. NORAL-D uses something called normal regularized latent diffusion learning. Bit of a mouthful, I know.
Well, yeah, just a bit.
But basically, it means the system builds the 3D shape step by step, constantly checking back against the normal map to make sure all the surface details, the bumps, the curves, the angles are spot on.
So the normal map keeps the diffusion process honest, geometrically speaking.
Perfectly put. It ensures that high fidelity, that precision in the final geometry.
Okay, NIRL for the normal map, NORAL for the geometries, the three parts. What's the third? Must be the data, right? You mentioned detail first.
Spot on. You can't have great AI without great data. The third vital piece is the detail-verse data set. And this isn't just scraped data, it's a custom-built, high-quality synthetic data set.
Synthetic, generated by computer.
Yes, 700,000 diverse 3D assets. Crucially, because it's synthetic, they could ensure it has really rich, clean geometric details perfectly aligned with its 2D views. That's often missing in, say, human-scanned or crowdsourced datasets like Objaverse XL, which can be noisier or less consistent. Detailverse gives the AI that deep understanding of form.
Wow, 700,000 assets specifically designed for this. That's huge.
Yeah.
Okay, so pulling it all together, for you, our listener, the creator out there, what's the bottom line? What does this mean in practice?
It means, frankly, superior performance, significantly better results. They ran user studies, got feedback from professional 3D artists and regular users, too.
Yeah.
And the consensus was clear. Hi3DGen excelled at capturing fine details and maintaining geometric accuracy. It consistently outperformed other leading methods. We're talking a noticeable leap in quality.
So it's not just marginal gains. This actually makes difficult things easier, or even possible for the first time for some people.
Definitely. Think about it. Getting a high-fidelity 3D model from one photo used to mean hours of manual modeling, or needing multiple photos, maybe expensive scanners. Hi3DGen takes a single snapshot and intelligently infers that hidden depth with really impressive accuracy.
And the applications seem huge.
Oh, absolutely. Rapid game asset creation, visual effects for film, much better 3D models for online shopping, detailed stuff for 3D printing, even, cultural heritage digitizing artifacts from just photos.
Is it easy to access?
Yeah, they offer online demos, and you can install it locally too. It's worth noting, though, it still has some limitations.
Yeah.
Very, very complex shapes or images with really extreme or weird lighting can still be challenging. It's not magic, but it's a big step.
This deep dive really makes it clear. Hi3DGen feels like it's genuinely democratizing high-fidelity 3D creation, making it accessible.
It really is. It offers a powerful new path forward using those normal maps as this effective bridge to get amazing detail from surprisingly simple input.
So for you listening, it fundamentally changes the game in digital creation. Makes you think, doesn't it? With a tool like this becoming available, how might it spark totally new kinds of art or new ways of telling stories or maybe even visualizing complex science in the years ahead?